Section 12.5, sigma notation in the nth term. We're going to start with talking about sigma notation. Sigma notation is notation used to indicate a sum or a series. So rather than, in the past writing out each individual term and then, writing out 4 or 5 terms and then the ellipsis, the dot, dot, dot at the end, we don't need to do that anymore because there's a way that we can kind of get around that. It's called sigma notation because it uses the Greek letter sigma. If you've ever been on a college campus before, driving around the fraternity areas, you see the Greek letter sigma quite often. It looks like an E. Okay, so that's the Greek letter sigma right there. That's supposed to be a little like that. Okay, so this is sigma notation. The sigma is the E. Usually, not usually, every time you write sigma notation, you need to write something like n equals 1 down there, and k up on top of it, and then a sub n down there. So, what this all represents, the a sub n, that is your expression for the general term of your series, for the general term. And I apologize if that's kind of hard to read. Expression for the general term of your series. So we draw that arrow in there. So a sub n, that's your expression for the general term. The number on the bottom, the n equals 1, this is your starting value for n. So if we're starting with the first term, that will say n equals 1. If we're starting with the fourth term, it will say n equals 4. If we're starting with the 10th term, it will say n equals 0. Okay, so whatever we start with, whichever term we're starting with, that will be on the bottom. Then up top, the k value, this is the maximum value of n. So this could be 6, it could be 10, it could be infinity. If it's a specific number like n equals 1 to 6, we're looking for the sum of the first 6 terms, the first, second, third, fourth, fifth, and sixth terms of our general series. Okay, one more vocabulary term, the index of summation. It's the variable used with sigma notation. Usually it's n, sometimes it could be k, sometimes it's b, sometimes it doesn't have to be any specific variable. Usually though you will see n. Okay, so it'll be n equals 1 to something of how this goes. Okay, so what does sigma notation represent? Well, if we were to write out sigma notation, so let me write this out here. So we got the E with a little tail there. Let's try that again. So there, from n equals 1 to k of a sub n. What that really means is this is equal to the first term plus the second term plus the third term plus and so on until we get to the kth term, if that's a word, k term. Okay, so up until whatever this number is. If it's the fourth term, then this will be the first, second, third, and fourth term. If it's the 10th term, we'll go first, second, third, all the way up to 10. Or the 50th term, all the way up to 50, so on like that. Okay, what it really means, let me write this in purple, it's the sum of the first k terms of a series. Okay, it's the sum of the first k terms of a series. So if it's the first 10 terms, then it's the first 10 terms. If it's the first 20 terms, it's the first 20 terms. If it's the first 3 terms, then it's just the first 3 terms. Okay, the sigma notation will tell you it's never going to be blank. It's never going to be ambiguous or unclear how many terms it wants you to add together. It will specifically or explicitly tell you in the notation. Okay, so let's expand each expression and then find the sum. So I got a couple of examples here. With the first one here, we're finding the sum of 3 to the b plus 1 from b equals 4 to 7. Okay, so we're starting this time with 4 instead of 1. The first couple of times I wrote this, it was always n equals 1. Well, this time it's going to be 4, and we're using b just because that's our variable. And so let's expand this out, and we'll try to figure out what this is equal to. So I'm going to kind of use 2 lines here. So we're starting with 4, so we're going to have 3 to the 4th, because b is our variable, and we're going to start with 4. So 3 to the 4th plus 1 plus, we'll go back to red, 3 to the 5th plus 1 plus 3 to the 6th plus, let's try that again, get rid of that, plus 1, that's 6. And then the last one plus, I have to squeeze this in here, 3 to the 7th plus 1. The reason we're stopping at 3 to the 7th is because we're stopping with the 7th term. So we're starting with the 4th term. in our series, and we're stopping with the 7th term, and we're going to add these 4 terms together. Now, 3 to the 4th plus 1. 3 to the 4th is 81, plus 1 gives me 82. 3 to the 5th plus 1 is 200, whoops, not equals, sorry. 382 plus this is 244. 3 to the 6th plus 1. 3 to the 6th is 729, plus 1 gives me 730. And then 3 to the 7th is 3243, plus 1, I don't know why I keep writing equals there, that's going to be plus 2188. I apologize, it's 2,187. And then when we add them all together, then what we're going to get, and I'll do that in orange here, when we add these together, we get 3,244. This is the first, the 4th, 5th, 6th, and 7th terms of this series right here add up to get 3,244. Let's try a second one here. So from n equals 1 to infinity. So we're adding up all of the terms in our series here. So what does this look like? Well, if we write this out, this is going to be 2 times 1 over 3 to the first power plus, go back to the red here, 2 times 1/3 to the second power plus 2 times, oops, let me undo that, keep the notation consistent, 2 times 1/3 to the third power plus, and this goes on forever. So now how do we add up an infinite sequence? Well, this is not a sequence, this is a series. We add up an infinite series if it's geometric. This is geometric because this is the formula, a sub 1 times r to the n power. Since this is a geometric series, we can use the formula we learned in 12.3, section 12.3, the infinite series. This is infinite because it goes on forever. Okay, so if we recall, let me switch back to blue. We're going to recall the sum of an infinite series in section 12.3. Okay, that formula, remember, is S equals A sub 1 over 1 minus R. Okay, we know the first term. Let me switch back to orange here. We know the first term is 2/3 because 1/3 to the first power is 1/3 times 2 gives me 2/3, and then the common ratio here is what's being raised to the power. Okay, so it's 1/3 every time. So the common ratio here is 1/3. So the sum of our series is equal to 2/3 over 1 minus 1/3, and 1 minus 1/3 is 2/3. So we can say this is 2/3 over 2/3, and any number divided by itself is 1. So if we add up every one of these terms in this series, we would eventually get to 1 if it were at all possible. Let's take a look at a story problem here. During a 9-hole charity golf match, the following proposition is presented. The loser of the first hole will pay $1 to charity. Each subsequent hole will be worth twice as much as the previous hole. Question number 1, how much is the 4th hole worth? Well, let's see if we could list it out. So hole number 1, and then hole number 2, hole 3, hole 4. If we wanted to list them out farther, we could. We know the first hole is worth $1. Second hole is worth twice as much, so we go times 2, so that would be $2. The third hole is going to be worth twice as much more, so that's $4. Times 2 to get the next one, so the 4th hole is going to be worth $8. Okay, so that's the first question. How much is the first hole worth? It's $8. I guess I don't need the $ and the word dollar, so I'll just leave it at $8. Now, is there a way we could figure this out using the geometric or arithmetic series and sequences? And the answer here is yes. Since we're multiplying by 2 every time, we can think about this as a geometric series. Remember the formula for a geometric series, a sub n is equal to a sub 1 times r to the n minus 1 power. Okay, so the formula a sub n, the first term here is 1. The common ratio is 2 to the n minus 1 power. So if we're looking for the 4th term here, going to kind of just give you a more analytic way to figure this out. We're looking for the 4th hole, which is the 4th term in our series or our sequence. So we can say a sub 4 is equal to 1 times 2 to the 4 minus 1 power, which is really 3. So 1 times 2 to the third. 2 to the third is 8, so we can say the a sub 4, the 4th term in our series or our sequence, is 8. So that's kind of the mathematical way we can figure out that the fourth hole is worth $8 without having to list out every single hole, or especially if we were looking for the 7th hole or the 8th hole, then we'd be doing this for quite a while. If we can figure out our formula, then it's just a matter of plugging in our numbers and getting our answer. Question number 2, how much would a player pay if he or she lost all 9 holes? So what it's really asking for is the sum of all 9 holes. So if we were to list out every hole from 1 through 9, what would the whole total be worth if we were to lose every hole? Okay, so now we're going to use that sum formula just like we did right back in here. Okay, it's not quite exactly this formula, but it's very similar. This one's a finite geometric sequence. So the formula here, this goes back to section 12.2. Sum of a finite geometric sequence is equal to a sub 1 minus a sub 1 r to the n power over 1 minus r. Okay, this time we're looking for all 9 terms. We're looking for the sum of all 9 terms, so we can say s sub 9, the sum of the first 9 terms, is equal to the first term, which is the first hole, which is worth $1, minus $1 times the common ratio of 2 to the n power is 9, all over 1 minus 2. Now this is something you can type in your calculator. Not saying you have to do this by hand or even in many steps. You can just put things in parentheses in your calculator. Hopefully you remember how to do that. If you were to lose all 9 holes, you would owe charity a grand total of $511. Okay, question number 3 then. Represent the sum using sigma notation. So rather than using the formula, or rather than writing out all of this or writing plus in between all of them, let's use sigma notation here, because that, after all, the section is about sigma notation. We need to start with our sigma, so we don't have a whole lot of room, so I'm going to write this a little smaller than what I would like to. So there, so sigma. We're starting with the first hole, so we're going to relate this back to our geometric formula here. Okay, so our first hole was n equals 1. Let me go back to my pen, n equals 1. The last hole, we're not looking for all of the terms, we're looking for the first 9 holes, so 1 through, we're going to go up to 9, so the first 9 terms of our series, or our sequence, would be series because we're adding them together, because we're looking to get to this. We're going to use this formula right here. Okay, so 1 times 2 to the n minus 1, so 1 times 2 to the n minus 1 power. And that's all there is to it. Once you can put your general term, just like we've done in the past where we get our general term in terms of n, this is your answer. We're looking for the sum of the first 9 terms of this formula or this series, and that's all there is to it. You don't necessarily need the 1 right here, just because 1 times something is going to be that same thing. So if you wanted to write this without the 1, you certainly can. So we'll make sigma from n equals 1 to 9 of 2 to the n minus 1 power. Both of those are fine. Okay, let's try a couple more here. Express the series using sigma notation. So 16 plus 19 plus 22 plus 25, all the way up to 61. Now we need to know the formula for the general formula for the term in the series. Okay, and remember, we do not have to start with n equals 1, so we don't have to call this the first term. This could be the 10th term, and that's what we're starting with, or the 15th term, or the 20th term, or the 3rd term. It doesn't always have to be n equals 1. Okay, so keep that in mind. So 16, 19, 22, 25. It looks like we're counting by 3s, but the problem is that they're not multiples of 3. They look like they kind of look like one more than multiples of 3, because I'm thinking multiples of 3 being 15, 18, 21, 24, and then 60. So what we can say is that each term in our series here, each term is one more than a multiple of 3, than a multiple of 3. So we could say 16 is equal to 3 times 5 plus 1. We could say that 22 is, don't want to use a parenthesis there, 22 is equal to 3 times, 3 times 7 would be 21 plus 1. We could say that 60 is equal to 3 times 20 plus 1. So is there a way we could write out the general form of our series? And the answer definitely is yes. We could say that a sub n is equal to 3 times our nth term plus 1. This really hasn't helped us in terms of writing it in sigma notation yet because we haven't filled it in. It does help us a little bit. I guess I shouldn't say it doesn't, because it does help us. Let me switch to blue here. So let's fill in our sigma notation. We know it's going to be sigma. We're going to fill in these numbers on the top and the bottom of the E looking thing. We'll fill that in last. This is our general term. Okay, this is what's going to go after the E. This is going to be 3n plus 1. The question is, what are the two numbers going to be? We know we're using n, so it's going to be n equals something, and then we need to fill in this number. 16 is the first term in our series, and we could say 16 was equal to 3 times 5 plus 1. So I think it makes sense to replace n, or to start with n equals 5 in this case. Like I said, we don't have to start with 1 every time. We can start with something else, and this time we're going to start with 5, because 3 times 5 would give you 15 plus 1 gives you 16. So the starting term in our series is going to be the fifth term, which is 16. And if we go all the way up to 61, like we did here, whoops, this should have been 61. I apologize, 61. 61 is 3 times 20 plus 1. So the last term in our series is actually the 20th term in our partial series that we're looking at. So the number that goes on top of the sigma is going to be 20. And this right here is your final answer, where n equals 5 to 20 of the sum of 3n plus 1. And that's your answer if we're writing it in sigma notation. Whoops, let's try another one here. 15 plus 24 plus 35 plus 48 plus 63. Now, this one, as you're looking at it, what I see here, I see almost perfect squares, thinking 16, 25, 36, 49, 64. Again, like we've said before, this isn't necessarily something you're going to see right away. This might take you a few minutes to find the pattern, and that's okay. Just stick with it, and it will come to you. Okay, so what I see here is each term is one less than a perfect square. One less than a perfect square. Okay, so we can say that 15 is equal to 4 squared minus 1. We could say that 35 is equal to 6 squared minus 1. We could say that 63 is 8 squared minus 1. So what we can say then for our general term, we could say that a sub n is equal to n squared minus 1. Now the question is, when we write our sigma notation, what is our starting value? What is our maximum value for n? Okay, so let's fill in some sigma notation here. I'm going to go to blue. So sigma notation, what are we starting with? Well, the term 15 looks like 4 squared. And if we think about this, I think it makes sense to say that n is equal to 4. I guess I missed my little brackets there on the E. Okay, so the starting term, let me erase that. That's a disaster of handwriting. N equals 4. What are we going to? What's our maximum n value? Well, if you look at our series, there isn't one. In this first one here, 61 was the end term. There's not a plus ... on the end, so that makes sense to go to 20. If this one here goes to, well, it goes forever because it says plus and then ... it just goes forever. So if it goes forever, our maximum value is going to be infinity. So above the sigma sign is going to be the infinity symbol, and that's okay. You can have that. And what's the formula that goes after the sigma? Well, that's going to be this one right here, n squared minus 1. And there is your answer for the series written in sigma notation. The last item of business in section 12.5 is the idea of factorial, n factorial. Okay, n factorial, or any factorial, is the product of descending integers from n to 1. The key here with factorial is you're never going to use decimals or never going to use fractions. It's all integers, all whole numbers, positive integers from n to 1. So it's denoted n with an exclamation point. Now, when I used to teach in the front of the classroom, I would yell. Does anybody know how to say this? I would yell like n, just very loud and scary, but it was funny. I can't do that in a video, so I'm not going to do that. Factorial is whatever number it is with an exclamation point. That's what factorial means. You can do factorial in your calculators. If you hit, so if you want to do 2 factorial, you're going to type in the number 2, then you're going to hit math, and then you're going to scroll over 1 to the probability menu, over to the right one. Those are the menus at the top, and then option number 4. So math, probability, over to probability, and then option number 4, and then once you have that, it'll put the exclamation point. You can hit enter, and the calculator will do it for you. But 2 factorial, what that really means is it's just 2 times 1, which is 2. 3 factorial is going to be 3 times 2 times 1, which 3 times 2 is 6, times 1 is 6. 4 factorial is 4 times 3 times 2 times 1. Well, we already know 3 times 2 times 1, that's 6. And if we take 6 times 4, that's going to be 24. 5 factorial is 5 times 4 times 3 times 2 times 1. We already know 4 times 3 times 2 times 1, that's the line above. So 24 times 5 is going to be 120. You can see that factorial gets very large, and I mean very large, very fast. 6 factorial, if you wanted to write it out, you can. 6 factorial is going to be 120 times 6, which is 720. 7 factorial, this is in the calculator, 5,040. And then 8 factorial, if you wanted to go that high, 40,320. So you can see we go from 2 to 6 to 24 to 120 to 720 to 540 to 4,320 extremely fast. Okay, so this is not necessarily something you're going to be able to do, calculate by hand. Use your calculators here. In general, n factorial, it's equal to this. It's equal to n. So if we started with 10 factorial, we'd start with 10, and then we'd go to 9. So then it'd be n times n minus 1, and then n minus 2, and then n minus 3, whatever it might be, all the way down into 3 times 2 times 1. Okay, so it always ends in 1. It always starts from this number and works your way down, all the way down to 1. Okay, so just so you have that in the back of your mind. So let's try one example here. Express the series using sigma notation. So 2 plus 6 over 2 plus 24 plus 24 over 3 plus 120 over 4 plus forever. Okay, let's think about this. The denominators. I don't have a denominator in the first one, but we can assume it's 1. If we look at the denominators, it looks like it's just counting by ones. So we can say the denominators are, we'll just say n, because it's the nth term. The first term has a denominator of 1. Second term has a denominator of 2. Third term has 3. Fourth term has 4. And it would continue. The numerators, let me switch to purple here. The numerators are, well, the first term looks like it would be 2 factorial. And the second term looks like 3 factorial. The third term is 4 factorial. The fourth term is 5 factorial. So each term is the next number up factorial. Okay, so the first term is 2. That's 2 factorial. The second term would be 3 factorial, which is 6. The third term would be 4 factorial, which is 24. The fourth term is 5 factorial. So we can say the numerators are going to be n plus 1 factorial. So if we want the fifth term, we would find 6 factorial, and that would be the numerator for our fifth term. So it would be 720, and eventually over 5, because we got to think about our denominator as well. So what's our starting value? So we'll say starting value is n equals what? Well, it's the first term, and our n value is 1, so the n value is 1. The maximum value, the number that goes on top of the sigma symbol, maximum value is, well, if we look, this goes on forever. So we can say that the maximum value is infinity. So once we've identified the starting value, we've identified the maximum value, we could write the general term of each, or the general form of each term if we wanted to. Let's go ahead and do that real quick. A sub n is equal to, the numerator is n plus 1 factorial. The denominator is n. So this is our general form for each term. Now that we have all the vital pieces of information, let's go ahead and write it in sigma notation. So let me switch to blue here. Oops, I'm almost out of space here. So we're going to have sigma from n equals 1 to infinity of our general form. And we're not going to say a sub n, we know what a sub n is equal to. So let's write this out. We're going to have n plus 1 factorial over n, and that right there is your final answer.